Hello and welcome to the latest in our Mott webinar series. Today we are talking about achieving smoother flows and reducing particulate in air-driven pumps using our Mott's engineered solutions. Your speakers for today we have John Rosenberger, Applications Engineer Extraordinaire, and Greg Tedeschi, Product Marketing Manager Extraordinaire. I'm Rosina, I'm in marketing, but I'm just your intro and ending person today. So I'm going to start with some housekeeping. During the webinar, you will click on the little air talk bubble to ask questions, and you can click on the document to download resources. And without further ado, I will hand this over to our gentleman here to talk about Mott and air-driven pumps.
Thanks, everyone. This is Greg Tedeschi, the Healthcare Product Manager for Mott. Just a little background about who Mott is. We've been in business for 60 years now, making a wide variety of products for some pretty demanding customers, from NASA to some of the larger Fortune 100 companies. We have the largest install base of porous metal filters and fluid controls across many different applications and industries, ranging from even the Mars rover to implantable medical devices. We have the most extensive metal alloy selection for this porous material for tough operating conditions such as high temperatures and even corrosive environments. And we also have, relatively new to us, the Customer Innovation Center that is becoming the hub for industry-leading innovation in porous filtration and flow control, with the latest lab equipment and new technologies like additive porous manufacturing. So just to go over our agenda today, we will look at considerations, what you might consider for proper flow control and filtration in your fluidic system design, the advantages that porous metal may bring to that design, more specifically, how to reduce particulate and achieving smoother flows in air-driven pumping or air-driven pump systems, and then delve a little bit into next generation development of 3D printed porous and using computational fluid dynamics, and then how you can work with us at Mott for your unique challenges, and we'll wrap up from there. So with that, I'll hand it over to John.
Thanks, Greg. I've been with Mott Corporation for many years, the majority of that time in gas filtration, so I'm happy to be talking about that today. Okay, so when you're looking at designing a system for flow control and filtration, there's a few steps that we look at. The first being we are looking to achieve laminar flow, which has many advantages in your system. And with our porous metal, we're able to achieve a very tight pore size distribution from part to part and within media grade selection. So that contributes to the laminar flow characteristics of the material. We have methods and manufacturing techniques to be able to provide an accurate and repeatable flow performance given your system conditions, and we'll talk a little bit about that later. And again, given your system conditions, we can look at what is the proper media grade, what is the proper nominal pore size that will work best in your system to provide the best flow control and filtrate and balance that with the filtration efficiency. And then of course we are always looking at the hardware to make sure it will connect to your system properly. We make parts with standard commercially available fittings, and we can also customize to meet your specific needs. And finally, the compatibility of the material, both the hardware and the porous metal, is something that we always take into consideration. So now we'll talk a little bit about the advantages of porous metal for flow control. So with gas filtration, there's a common misconception that it's the same as liquid filtration, which it is not. Liquid filtration is basically a surface phenomenon where particles are captured on the surface of the material. And gas is very different. There are several different capture mechanisms as we have listed here. And the second most important difference is that with gas filtration, the capture mechanism, the mechanism by which the particle is captured within the filter material is size dependent. And you can see from the list, our material efficiently captures particle sizes down to the submicron level all the way up to several microns and above. So this slide here kind of shows if you look at that porous media thickness, that would be the material depth that the gas flows through. And that's a very important concept. So you can see that there are 5 different illustrations, and there's a reason there's 2 interceptions, but I'll walk through it really quickly. Diffusion is the smallest particle size, and that covers the submicron particles. And those particles are so small that they achieve Brownian motion based on the velocity of the gas stream that they're in. So they're bouncing around within the depth of that material and will eventually be captured on that material just because of the random motion of that part. The next size up would be the interception, and that's where the particle is large enough so that at some point within that tortuous path of the material, it will come in contact. It tends to want to ride the gas stream, but because the structure of the material is a tortuous path, it will come in contact. The third, and the reason there's 2 of those is because that, and you can see that there are in different depths in the material. That's what we call the most penetrating particle size, because they tend to want to stay in the gas stream and travel deeper into the porous material. The next larger size up is inertial impaction. That's for the particle sizes that are large enough so that they would have enough inertia as they are in the gas stream. They would just exit the gas stream and come in contact with the porous material much sooner than the smaller diffusion and interception particles. And then the final is sieving, which is the same as liquid, where the particle size is larger than the actual or the nominal pore size of the material, so it never enters the material. So it's captured on the upstream side of the filter. So here we'll talk a little bit about porous metal restrictors versus flow orifice. As we saw in the last slide, the porous metal restrictors have hundreds of flow paths depending on the size and the media grade. So there are many paths that the gas will flow through. So with an orifice, you have one hole, so that creates a higher gas exit velocity because you're putting the same volume of gas through one hole versus splitting it through many. This can also create a problem with clogging because you again have one hole, and with an orifice, your accuracy is defined by the accuracy of the ability to drill the size hole that you're using for the orifice. With porous metal, we have the manufacturing capabilities to tune a restrictor or calibrate a restrictor to whatever your pressure and gas and flow conditions are. So we can much more accurately dial in to your specific system conditions. And also a secondary benefit of a porous metal flow restrictor is it does act as a filter in addition to a flow control device. So this slide is at the bottom part of that slide shows the SEM photomicrographs of a range of our media grades from 0.2 micron. And by media grade, that we refer to that as the nominal pore size. There is a pore size distribution. They're not exactly all the same size, but we control our powder metal and our manufacturing techniques, our sintering and compaction techniques, so that we have a very tight distribution of pore size. But you can see these are all done at the same magnification, and you can see that the vast difference between a 0.2 media grade and 100 media grade. The pore size are vastly different, which impacts your pressure drop and your filtration efficiency. We have on the top part of the slide, we show some of the many different configurations of hardware. We specialize in customizing hardware. We've done many different. We use commercial hardware and anything that needs to be customized for your application. And finally, these are our main. Stainless steel is our primary material, but we also have several Hastelloys, Inconels, and some of the more exotic materials. And we do have the ability to customize alloys if that is the case. So if there are applications where you think you need some special alloy, you can come talk to us and we can see what we can do.
So one of the things we want to do is delve a little bit deeper into a specific application in this webinar, specifically achieving smoother flows and reducing particulates in air-driven pumps. And so, the application itself of an air-driven pump, the goal here in a lot of applications in life sciences may be to achieve smoother flows and reduce particulate contamination with Mott restrictors. And so if you think of something like flow cytometry, where you might want to flow a solution at a very constant rate with low pulsation, without any contact from a diaphragm or a piston head, a air-driven pump might be an ideal solution in that case.
Okay, so to that point, we would work with you to figure out what kind of flow rates you're looking for. Our flow rates range from very high, 100 liters a minute, down to very low SCCM. We have a broad range of temperature capabilities. We have a class 100 clean room where these parts can be made in a very clean environment. We calibrate, we actually make the restrictors to 6 inert gases, including nitrogen, argon, and so forth. And then we have calculations where we can correlate if you have a unique gas. And of course, we actually test with air, of course. And then we can customize in various different hardwares, as we've discussed. So when you're specifying a restrictor, these are the 5 key attributes that we need to know. First of all, what gas are you using? In many cases in these pump applications, I suspect it might be air, and that's fine. We need a flow rate, whether it's in standard cubic centimeters per minute or standard liters a minute, or whatever your flow, we can do whatever conversions. We're going to need to know what inlet pressure you're going to be using, and then we're going to need to know what outlet pressure. Typically, and most common, it would be to atmosphere, but if we can size and design restrictors that run to a downstream pressure or to a vacuum situation. And then hardware, we need to know what is it, how are we going to connect our part into your system. So another way to integrate porous metal into your pump systems would be a simple disc, where we would work with you to figure out what your pressures are, what flow rates you're looking at, and what kind of filtration efficiency you're looking for, what kind of particle sizes you want to capture. And we can select a media grade and create a disc that will meet those specifications. We can install it into whatever hardware you want. And again, going back to the very tight control of the pore size, which plays into the maintaining the filtration efficiency that you're looking for.
So just to touch on some of the other life science applications that might be using porous media technology that Mott has worked with in the past, looking at things related to flow control, low flow drug delivery. So perhaps a subcutaneous device that delivers a drug to a patient for many hours or many days, gas control and anesthesia delivery, GC or gas chromatography, regulating the gas flow in those analytical instruments, and HPLC or high performance liquid chromatography, where you're focusing the flow of the mobile phase in an analytical application. On the filtration side of things, various gas delivery systems, surgical devices, and even advanced diagnostic devices.
Okay, we're going to just touch briefly on some of the exciting new stuff that we're working on here. First of all, 3D printing porous. So the history of 3D printing or 3D solid printing is, the challenge has always been to remove porosity from the solid material, because that will make the part stronger. So we've kind of turned that on its head, and now we're saying let's add porosity and make that a flow part. And we have done that, and we're working on many different unique configurations, as you can see from some of the pictures. And the advantage of that is on some of those parts you're getting a lot of extra surface area for your, which will help reduce pressure drop and increase flow particle efficiency capture. We're able to control the way the part's printed. We control the pore sizes very tightly. So again, you get a very consistent part. One of the most exciting things is that we can make parts where we have the porous metal printed right to a piece of solid material in the picture on the right, which enables you to take the part and either put O-rings on it or weld it. So it's a single construction. Our conventional way of joining porous metal is either with welding or press fit or sinter bond, but this takes that extra process out of it and can makes for a more efficient product. Yes, and so the other area that we're looking at and working in is computational fluid dynamics. This is where we can take models of your system and we can put them into our system and run simulations on different process conditions that you're interested in learning about. And what this does is it gives us a better idea of where we want to start the project. It potentially reduces multiple prototype phases where we're just trying to guess where to go, and ultimately it will hopefully make the project timeline shorter and reduce costs, and hopefully ultimately reduce the cost.
So I just wanted to touch on at this point, how you can work with us or collaborate with Mott. So one way is to visit us in person at Mott's Customer Innovation Center. So here on site, you can receive particle science training and design consultation from our engineers and our material scientists. You can work with us in real time designing new prototypes in our rapid prototyping cell, and get really hands-on with lab testing sessions to see how we can optimize your design. Conversely, we can visit you at your site to conduct a technical workshop. What we would do is bring in-depth filtration and flow control training from our Mott engineers like John. Problem solving tailored to your company's needs. So we want to know in advance what you're working on so we can be prepared and have meaningful discussions while we're there. And then break out into one-on-one sessions with your engineers and Mott's engineering team. So there might be multiple groups that there might be multiple projects where we can get focused in one-on-one sessions.
Yeah, Greg, if I could add to that, I've been on 4 of these technical workshops in the last few months, and it's great to get a room full of engineers talking about ideas, and it's amazing how things one can feed off the other to generate ideas. So right. It was very, very helpful.
Great. So
this is just a list of some of the things that we do here. We can You know, we can work with anything that you're looking at as far as porous metal or filtration. So there's we have a lot of lab capabilities. We have a lot of high-tech equipment. We can analyze materials, and there's lots of things we can do.
So just to recap, in collaborating with us and how to reach out to us online, you can learn more about our engineering services on mottcorp.com and download our Mott capabilities brochure, or contact us directly either by web form or just pick up the phone and call us.
All right, thank you, gentlemen, very much. That was very informative and a great webinar. For those of you listening, if you'd like to get in touch with John or Greg directly, we have their email addresses here. I just tried to, oops, click on the, there we go. I won't get rid of it too fast. I just tried to click on the link and it wouldn't go through for me because I'm in presentation mode, so I apologize for that. But this is how you can get in touch with these gentlemen directly. And again, if we go back, the ways that you can get in touch with Mott in general, the contact form is great for those engineering services projects that you may have, or getting on site, or getting us on site with your team. Thanks very much for joining us, and we hope you join us for the next series.